All right, so what I want to do now is to use our deeper understanding of how to determine if triangles are congruent to study isosceles and equilateral triangles. So before we kind of start proper, I want to make a comment about congruence and a subtlety that we really overlooked up until now. So I want to kind of, in a sense, extend the concepts of congruence. Extension of the concept. It's not really an extension, it's just not something that we thought about particularly before, and it's something that you can easily be confused about. It's not talked about really in the textbook, so it's easy to miss. Okay, so two figures are congruent. Well, informally it's pretty simple. It's just if they have the same shape and size. The same shape and size. But we want to extend it a little bit. And basically what we want to do is to take into account the fact that if I have triangles, for example, which are mirror images of each other, then if I was to apply these kind of side angle side criterion, they would be the same, right? Things would just be reflected. So I want to also include the concept of mirror images, right? So, or one has the same size and shape, as the mirror image of the other. As the mirror image of the other. So really the first concept is the one we thought about first. So just as examples. If I take kind of just a triangle, say a right angle triangle like this, then what we're used to is just the same basic thing, maybe in a slightly different position. So I don't know, something like this. All right. Those are most definitely congruent. I can superimpose one on the other perfectly. It's all good. Okay. However, this triangle is also congruent to its mirror image now. Ooh. So if I was to draw basically a triangle which looks very similar but reflected, so that would technically be a little bit different, but we're going to decree that it's congruent, right? So these two are congruent as well. So this is the mirror image. The mirror image. Okay, so I'm just telling you that because it's an important subtlety and one that you can kind of overlook. And I should say that to check congruence of triangles, all of our criterion are exactly the same. So SAS, ASA, and AAS, these criterion all still hold. Okay. So let's think now about isosceles triangles. So definition. An isosceles triangle, something we're very familiar with, but let's do it really carefully. Right, so I'll just draw a picture to illustrate what an isosceles triangle looks like. So an isosceles triangle is going to be one where two of the sides are the same. Nice and simple. Okay, so if I have A, B, C here, let's label this length B and this length B. This guy is an isosceles triangle. Okay, two sides are equal. Two sides are equal. So this is the definition. It's involving sides. So let's take two angles here. So we want to come up with criterion to guarantee that a triangle is isosceles. So let's take these two internal angles. I'll call this one alpha and I'll call this one beta. Okay, so I'm going to call these the base internal angles. Okay, so first of all, theorem. So this is going to be very obvious from a kind of a visual perspective, but we want to prove it carefully. So in any isosceles triangle, the base angles are equal. The base internal angles are equal. So in this notation above, alpha is equal to beta. So I think this is very obvious intuitively, right? How could they not be, right? You've got this symmetry, right? There's no way these guys could be different if that and that are the same. So there's some feeling here that it's very obvious. But as always, I need to prove this carefully. And to do that, I need to use something I've already developed. So we're pretty used to a standard procedure now. If I want to show things like lengths or angles are the same, it's very good to somehow construct two congruent triangles and then match up sides and angles. So if I take this picture, so let's just take this guy exactly the same. So I've got this guy here. So I want to show alpha and beta are the same. So it would be a very good idea to have two triangles that are congruent here so I can match things up. Now, I can kind of intuitively see that if I have an isosceles triangle and I kind of divide it straight down the center like this. So if I cut it down the center with an angle there, 1, and an angle there, 2, and let's make these guys an angle bisector. So intuitively, right, I get the feeling that this triangle here and this triangle here, these two triangles, are going to be congruent to each other. So if I can prove they're congruent, alpha and beta would match, so they'd have to be equal to each other. So the aim, maybe I should label the bottom point here, let's call it L. Kind of the aim is to show, well, really we need to show my two triangles. So the triangle ALC is congruent to the triangle BLC. If I can do that, then I can match up the angles. It's all the same. So to do this, what are we going to do? Well, first of all, we've chosen this straight line to be an angle bisector. So that's going to make angle 1 and 2 the same. So that's going to be useful. We're going to use an angle. Is there anything else we know? Well, we have the fact that these lengths are the same. That's kind of the hypothesis. We also have the fact that this length here is shared, or this side is shared by both triangles. So I can see kind of immediately these triangles have a side, an angle, and a side which have to match up. So I should apply the side, angle, side criterion. So let's do this carefully. So first of all, sides. AC is equal to BC. Okay, this is the hypothesis. It's a hypothesis because we are assuming it's an isosceles triangle. Next, the angles 1 and 2 are equal to each other. And I'm going to say by construction because we ourselves have drawn in the angle bisector, right? That's us imposing something else on my triangle. So by construction. Also, they've got a shared side. CL is equal to CL. Shared side, very nice. So what does this mean? Well, now by the side angle side criterion, my triangles are congruent to each other. And if you notice, this is exactly the reason that I was careful at the start talking about this kind of extension of congruence to include mirror images, because these guys are mirror images of each other, right? They're mirror images reflecting down that line there. Okay, so it's important we understand why I did this in the first place. So the moment that happens, we just have to match everything up. Well, matching everything up gives me what? Instantly, I have alpha is equal to beta. Awesome, proof. Okay. Awesome. So, isosceles triangle, the two base angles are the same. So let's think about this in reverse. So theorem. So this is going to be a criterion, in the sense it's going to give us a way to check if a triangle is isosceles. So if two internal angles of a triangle are equal, then the triangle is isosceles. So again, let's basically take this picture, but not assume it's isosceles to start off with. So proof. Okay, so what do we got? So what am I going to do now? Well, I'm going to assume the two angles are the same. So let's just assume these two are the same. So now I need to show kind of the opposite of what we had before. I need to show that that and that are equal to each other. So to do this, I think I should go through a similar procedure. But I need to decide on the kind of construction I'm going to do. Should I choose an angle bisector? Should I choose what should I choose? There's a few options here. There's a few options. I think it would be nice to choose a slightly different one than we did before. Let's do an altitude, shall we say. Okay, and I'll call this H down here. So this is us imposing a construction. We don't need to do this, but it's just nice for some extra examples. Okay, so we want to show these two triangles are congruent. All right, so again, the aim is nice and simple. Let's show that the triangle given by AHC is congruent to the triangle given by BHC. Then the sides match up, they have to be the same length, you're isosceles. Okay, so first of all, the angle at A, by assumption, is the same as the angle at B. That's the hypothesis. Very nice. Next, what do we know? Well, we can move across to this angle here. And in both cases, that angle is the same. So the angle AHC is equal to the angle BHC. It's equal to 90 degrees. And that's by construction, right? Because we are constructing the altitude. Next, there's a shared side. CH is equal to CH. Very good. CH is equal to CH. And what does that mean? Well, that's because it's a shared side, I should say. So now what do we know? Well, these three things are angle, angle, side, aren't they? So now I can use the angle, angle, side criterion to tell me that these guys have to be congruent. Now again, they're mirror images of each other though. They're mirror images. So that means, well, they are congruent. That means the corresponding sides match up. So first of all, AC would have to equal BC. They're the corresponding sides. And finally, what does that tell you? Well, that literally is telling you that your triangle ABC is isosceles by definition. Proof. There we go. So let's just summarize what we've done here. These two things tell me the following. Kind of overall conclusion. Summary. So I'll just do this visually. If I take a triangle, so I'll just draw kind of a random triangle, and I'll do alpha and I'll do beta here, and I'll do B and I'll do A here. Well, then alpha equals beta if and only if A equals B. That's what we've shown. The first theorem is showing it in this direction. Right, it's showing if the thing is isosceles and the base angles have to be the same. The second criterion we've shown is showing it in this direction. And this symbol is kind of if and only if. They are completely identical logically. So that's basically what we've got here. So it might be worth making sure this is very, very highlighted. Oh my goodness, what is that? Okay, that's a really useful fact. So what I want you to do now is to go to your workbook, example. So go to your workbook L119 and try questions 1, 2, and 3. So you should pause the video and make an attempt to do all of these. Okay, so we're going to do one of these questions. I'll do 3, because I think 3 is the most interesting. So what have we got? We are told we have an isosceles triangle and one of its angles is 40. So I'll draw kind of a vague picture. This is not to scale at all, I'm just doing it to make sure we've got something to hold on to. Okay, and let's label some sides. Let's label this one alpha and let's label this one beta. Okay, so it seems to me there are two options. Option A is, well, one of the two guys is equal to 40 perhaps, right? So let's say alpha is equal to 40 degrees. All right, remember an isosceles triangle, two of the sides are the same, so two of the angles must be the same at least. So if this happened, this would mean, well, we can work out the internal angles. It would be alpha plus beta plus 40 is equal to 180. But this would imply that, well, 40 plus beta plus 40 is equal to 180. So that would, I suppose, imply finally that beta is equal to 100, okay, degrees. So in this possibility, the angles are 40, 40, and 100. There is another option, though. The other option is perhaps neither of alpha or beta are equal to 40, they're equal to themselves. So if alpha and beta is equal to each other, that would imply, well, once again, alpha plus beta plus 40 is equal to 180, but now it would be 2 alpha plus 40 is equal to 180. Going through this, 2 alpha would equal 140, and finally alpha would be equal to 70 degrees. So in this case, the other option would be 40 degrees, 70 degrees, 70 degrees. So there are two potentials here. Okay, so let's now look at a special case of this, right? So again, definition. If we take an isosceles triangle, or we attempt to, what is that? We do an isosceles triangle. Okay, come on. So we take an isosceles triangle where all these sides are exactly the same. So if I do A, B, C, and I do A, this, of course, very familiar to us, this is called an equilateral triangle. A three-sided regular polygon. So all the sides are equal. So the definition is all the sides are equal. Theorem. In an equilateral triangle, all internal angles are the same. And they're all 60 degrees. Okay, so let's just go up a second to this. I'm going to grab this again, because this is going to be the key to showing this result. So let's kind of shrink this down, bring it over here. All right, so let's take my equilateral triangle, so proof. So let's think about this guy up here. So what have I got? Well, I've got my alpha, my beta, and my gamma, all that kind of business. Let's just go through it super carefully. So first of all, if I look at this, if I look at that side and that side, that would compare that angle and that angle. So this result tells me the following. So AC is equal to BC. That implies, well, the angle at A must be equal to the angle at B. And this is actually an if and only if condition, remember, right? What else do we have? Well, we could do it with this and this, I suppose. So AB is equal to BC as well. Well, that implies the angle at A is equal to the angle at C. They're all the same. So together, this tells you all the same. Very nice. So that's done, I suppose, almost. But what we do know is the following. The angle at A plus the angle at B plus the angle at C is equal to 180. It's the triangle. So that would imply that 3 angle A is equal to 180. And of course, that implies the angle at A is equal to 60 degrees. So proof. Very nice. So an equilateral triangle, all the sides are the same. Unsurprisingly, this works in reverse. So theorem. Theorem. This is really a criterion. Really a criterion. So in this case, if in a triangle all 3 internal angles are equal, then it is equilateral. Kind of really obvious, but same basic deal. So proof, it's just the same as above, really. It's done above because all of these things are if and only if conditions, right? So copy, it's just the same thing. If the angles are the same, so do the sides, right? So I'm just kind of same thing in reverse. just in reverse, which we know we can do because of the fact this condition is an if and only if condition. Proof. Oh my goodness. Okay. So why don't you now try examples 1 and 2. Example. So let's do workbook as usual, L120, do question 1 and do question 2. Try those. So pause the video and then come back to see me go through one of them. Okay. So let's do question 1 of these two. So what do we have? We have a, oh my goodness. We have an isosceles triangle, an attempt at one. We have an isosceles triangle, one of which the internal angles is 60 degrees. Okay? So let's think about this alpha and beta. So this guy is isosceles. That's part of the assumptions. So there are kind of two options again. Option A is either, well, let's say alpha is equal to 60 degrees. In this case, this would mean what? Well, beta would be equal to 180 minus 60, which is equal to 60 degrees, which tells you all the internal angles are 60 degrees. This tells you it's an equilateral triangle. Or second option, well, maybe they're the same. Alpha and beta are the same. Well, this would imply what? 2 alpha plus 60 is equal to 180 degrees. This would imply what? That 2 alpha is equal to 120. And this would imply that alpha is equal to 60 degrees, which would imply beta is equal to 60 degrees. Either way, it's an equilateral triangle. Bingo, right? So in both cases, it is definitely an equilateral triangle. Very useful fact. Okay, so that's a good place to stop. Yeah. See you next week.